In this lesson, we're talking about something else that you can do to a function or to a relation. In the last lesson, we discussed operations with functions, adding them, subtracting them, multiplying them, dividing them, and composing functions together. And in this lesson, we're going to start talking about taking the inverse of a function. First, we want to talk generally about inverse relations. So an inverse relation, or put another way, two relations are inverses of each other if every a comma b in one relation corresponds to a b comma a in the other. So for example, if I have a function or a relation where my x bubble includes 2 and 3, and my y bubble contains a 1 and a 5, and I know that the 2 goes to the 1 and the 3 goes to the 5. If I have that relation and this one, notice how the 2, 1 in the relation on the left corresponds to the 1, 2 in the relation on the right. Similarly, the 3, 5 in the relation on the left corresponds to the 5, 3 in the relation on the right. So we say that they're inverse functions now if, when I take the inverse of a function, the inverse of it is also a function. So we've talked about that vertical line test that you used in algebra to determine whether a relation was a function. Along the same lines, we can use a horizontal. Okay, it doesn't want to write on that. But you can use a horizontal line test in order to determine if a function has an inverse function. And remember that in order to use the vertical line test, you had to have a graph. Similarly, you can't use the horizontal line test without a graph. For the purposes of what I'm trying to indicate and what Desmos for some reason doesn't allow me to do, I'm using a different app to show you this. I'm using Geogebra. Feel free to check it out. It's at geogebra.org. Or you can download the app, Geogebra 5. So I've graphed the function in part A, and I said I wanted to use the horizontal line test to determine whether this function has an inverse that is also a function. So we're using the horizontal line test, and as you can see, I've graphed a horizontal line. It's right here. And I'm going to take my horizontal line and drag it up my function. And what I'd like you to be noticing is that at no point will I be intersecting my function more than once. And so you see that the instructions were simply asking, write yes or no. So the question once again was determine whether its inverse function exists. Yes, it will exist. Pause your video to work through the your turn below. So how do I find the inverse of a function? First of all, I want to make sure that the function has an inverse by doing that horizontal line test we just discussed. Step 2, it says replace f of x with y and then interchange x and y. So basically, you're going to switch the x's and y's. And then you'll get y by itself. And then you'll go back to our function notation and replace y with f of 1 of x, f to the negative 1 of x. And then we want to make sure that we state any restrictions on the domain of our function. And I'd hope that you'd notice that since we're switching the x's and y's, the domain of one function would be the range of the other. So we're going to determine whether something has an inverse function, and then we'll find the inverse function. So negative 16 plus x to the third. This is our graph. I still have my horizontal line here so that I can test it. And I might want to zoom out to make sure I'm not missing anything. But if I take this horizontal line and I slide it up and down my graph, it's never going to hit the function more than once. So this does have an inverse function. Since this does have an inverse function, let's figure out what it is. I replace the f of x with y, and then I switch the x and y. And then we solve for y. So I have x plus 16 equals y to the third when I add 16 to both sides. And then I need to take the cubic root of both sides, and I get that y equals the cubic root of x plus 16. And the problem is asking us to state any restrictions on its domain. Notice that we're taking a root of x plus 16, but we're taking an odd root of it. Notice, make sure that you're aware, that you can take the odd root of a negative number as much as you want. You're not taking the square root of a negative number, you're taking the cubic root, and I can multiply a negative number times itself an odd number of times and get a negative number. Okay, so there are no restrictions on the domain. And visually, let's take a look at the graphs of the original function and its inverse. So notice I've graphed the original function, it's graphed in red, and its inverse, it's graphed in black, and realize that the domain and range for both of them are all real numbers, negative infinity to positive infinity across the board. Part B, first thing we want to identify is whether an inverse function exists. So let's graph x plus 7 over x. Notice how it does pass the horizontal line test. So this function has an inverse function. So I know that this function has an inverse. Let's find it. Y equals x plus 7 over x. I switch my x's and y's, so x equals y plus 7 over y. And I've got to get my y's together in a way such that I would end up with just one y in this equation. But that y being in the denominator is kind of a fly in the ointment. So I'm going to multiply both sides by y. So I'll get that xy equals y plus 7, because remember, these y's cancel out. And now I'll bring my y's together, I'll subtract y from both sides and get xy minus y equals 7. And now because y is a common factor in the two terms on the left side of the equation, I can factor that y out and get x minus 1 left in that parentheses equal to 7. And now I divide both sides by x minus 1. And my equation in the end is y equals 7 over x minus 1. And I'd hope that you'd notice that this one does have a restricted domain. Notice that I have an x in the denominator and I can't have 0 in the denominator. So that means that x minus 1 cannot equal 0. So my domain is all real numbers, but x cannot equal 1. And one of the things that they want us to notice is the relationship between the domain and range of the function and its inverse. So let's take a look at the domain and range of that function. So my original function is graphed here. Get it kind of centered. My other equation, its inverse, was 7 over x minus 1. And so in the domain of my inverse function, which is green, this one here, we talked about how x cannot equal 1. Well, notice how in the blue one, if I take this point and drag it on over, my domain, my y, notice how it's getting closer and closer to 1, but it never quite seems like it's going to get there. So in my original function, over here, this had a range of all real numbers, but y would not equal 1. And notice how in its inverse, it's the domain that has all real numbers, but x cannot equal 1. So let's see if that relationship exists with our domain and range in the other direction. So in the original function, my domain was that x could not equal 0. So, and make sure that you understand why. In the original function, this one, x can't equal 0 because x is in the denominator and you can't divide by 0. Okay, so what I'm trying to get across is when I go back and look at that graph of the inverse, is my range going to be such that y cannot equal 0? Let's take a look. So my inverse is this green one, and I just want to look at that. And in my green one, what I'm trying to determine is if my range, my y values, cannot equal 0. So I'm just going to kind of pick a point and drag it over. And notice that as I'm dragging it along, it sure is getting closer and closer to 0, but it never seems like it's going to get there. And it doesn't. So we have verified that the domain and range of the original function correspond to the range and domain of its inverse. And you might want to pause this before I erase in order to do part C. Part C, before we try to find the inverse of this function, let's make sure that it is, in fact, going to be a function. So the square root of x squared minus 20. Let's graph that. So I graph the square root of x squared minus 20, and when I bring up my horizontal line, maybe it's hard to see, notice that it's crossing my function in two places. So this does not have an inverse function. So we're done for part 2C. I erased all of that for nothing because all we need for part C is the word no. No inverse function exists. So you may have noticed that when we find inverse functions, that they're kind of undoing each other. So one of the properties of inverse functions is if I take the composition of f of g of x and g of f of x, if those two functions, f and g, are inverses of each other, then that composition will always equal x. Show you what I mean. So if I take the f of g of x, that would be the f of 6 minus x over 3. So that would be taking that 6 minus x over 3 and plugging it in for x in my f function. So it would be 18 minus 3 times the quantity 6 minus x over 3. And then I would distribute that negative 3. So I'd have 18 minus 18. You can already see how things are going to start canceling out. And then plus, I have to multiply this negative 3 times negative x over 3. So that's why I'm writing a plus sign. Negative times negative is positive. And if I think of this negative 3 as being over 1, that 3 over 1 and that x over 3, those 3's are going to cancel out, and I just have x left. And I already kind of gave it away that this stuff is going to cancel out, and lo and behold, it's just x. So let's do it in the opposite direction. If I take the g of f of x, that means I'm taking the g of 18 minus 3x. So I'm taking that 18 minus 3x and plugging it into my g function. So I would have 6 minus 18 minus 3x over 3. Well, this fraction here, this whole fraction, is reducible by 3. All of the terms in the numerator are divisible by 3. So I can reduce this and get 6 minus, that 18 divided by 3 is 6. Again, you can start to see the things canceling out. Plus, because negative times negative is positive. And 3x over 3 is just 1x, or x. Again, this stuff cancels out, and it's just x. And I'm going to need some space in order to do part B. You may want to pause the video to make sure you've gotten from this screen what you need. I'm going to take the f of g of x. So that means I'm taking the f of this square root of x minus 10 quantity, and I'll be plugging that into my x function. So that will equal square root of x minus 10 squared plus 10. And when I take that square root and I square it, I get just x minus 10. And then I'm adding a plus 10 to it. I'm bringing this down. And those cancel out and I just have x. Let's do it in the other direction. Taking the g of f of x, I'd be taking the g of x squared plus 10, and I'm taking that x squared plus 10 and plugging it into the square root of x squared plus 10 minus 10. So the 10 minus 10 cancel each other out, and I have the square root of x squared, which will equal x, as long as x is greater than or equal to 0. Notice how that we have that restricted domain. Graphically, you may have noticed an interesting relationship about the inverse functions. They are reflections of each other over the line y equals x. So think about that equation, y equals x. What have we been doing every time that we take the inverse of a function? We switch the x and y together with each other. So that should kind of make sense. So here's my line of reflection that I'm drawing in for you. That's the line y equals x. And they're asking us to use the graph of the function to graph its inverse function. So let's just remember our geometry a little bit. We're going to take a couple of points off of our graph, reflect it over that green line that I've given you, and then just kind of connect the dots and make sure that it's following the same shape. So myself personally, I see this point, I see this point, and this point. All right, so reflecting them over that line, this one comes here, this one comes here, and this point doesn't have very far to go. It'll be there. And so when I connect those dots, naturally the reflection of a line will be another line. My answer is this line. We start the next example off along the same lines by graphing the line of reflection, which is y equals x. So that's this line here. And taking a few points from the function g of x and reflecting them over that blue line that I've just given you. Okay, so this one's a little bit more challenging. Maybe I would graph this point, do it in a different color though. And I know it's going to pass through that point. So because the curvature of this graph is so very similar to a straight line, I'm just going to use the one point that I got. Okay, so this line, this point here, when I reflect it over that blue line, comes here. So now my final graph looks like this.